Welcome back to the deep dive. Today we are getting into a massive conceptual shift in the world of large language models.
Pepper.
We've got this paper, LLaD 2.0, scaling up diffusion language models to 100B,
Hmm.
and honestly, it's like it offers a cheat code for building faster, more efficient foundation models.
That really is the core mission here. It's about understanding how LLaDA 2.0 gets around the traditional way of doing things.
Right.
You're used to autoregressive models, or AR, which write a sentence one token after another,
Yep.
sequentially.
Hmm.
LLaDA 2.0 is all about discrete diffusion language models, or dLLMs. Think of it like those image diffusion models you've seen, but for language.
Okay.
They basically refine a noisy draft of text until it's perfect, which lets them generate the entire output all at once.
Okay, let's unpack this because
Yeah.
if AR and DLLMs are fundamentally different architectures, how on earth did the LLaDA 2.0 team create a 100 billion parameter DLLM without spending, a fortune to train it from scratch? That sounds like trying to transfer the brain from an old car into a new airplane.
That's a great way to put it. The engineering trick here is what they call systematic conversion.
Systematic conversion.
They take an existing pre-trained AR model and they convert its structure into a dLLM. And this is so powerful because it upholds this idea of knowledge inheritance.
So they keep everything the original model already learned.
Exactly. They get to bypass that multi-year, incredibly costly training phase entirely.
So the efficiency isn't just in the final product. It's baked into the creation process itself by leveraging what's already there.
That's it.
But that conversion process, it sounds tricky. They couldn't have just flipped a switch, right?
Yeah.
The paper mentions this really novel training scheme, warm-up, stable, and decay, WSD.
Precisely. You can't just force the transition. They needed an adaptive training plan to sort of teach the old model how to think in this new diffusion way.
Okay.
And this WSD scheme, it's all about progressively manipulating the block size during the diffusion training.
That seems a little counterintuitive, going small, then big, then small again. Why does that specific sequence work?
Well, think of it like tuning a huge orchestra.
Okay.
The warm-up phase uses small blocks to just establish the basic diffusion structure. Then, the stable phase. That's the big one. It uses large-scale, full-sequence diffusion to make sure there's global coherence.
Locking in the big picture.
Right. It makes sure the whole model gets the new process.
Yeah.
Then finally, the decay phase goes back to compact blocks. This allows for, fine-grained control and refining all the little details in the output.
And the result of all that is the key advantage you mentioned, parallel decoding.
Yes.
So instead of waiting for the previous word, the model generates words at the same time, leading to much better inference speed.
And that's where you get superior performance and efficiency at this massive scale. And if we look at the models they actually produced, LLaDA 2.0 is clearly built for practical use.
Right, the two variants.
Two main instruction-tuned variants. LLaDA 2.0 mini at 16 billion parameters and LLaDA 2.0 flash hitting that 100 billion mark. But crucially, both are a mixture of experts, or MOE.
Okay, for anyone listening who's tracking deployment costs, this next detail is the real game changer. Why is MOE so important here?
Because MOE means the model is modular. When you ask it a question, only the specific experts, the parts of the model relevant to your task, actually activate.
Got it.
This just dramatically cuts down on the compute needed to serve the model. It's so much cheaper and faster to run in the real world than a dense 100B model. They also use standard steps like SFT and DPO for alignment, just to make sure it was ready for real-world tasks.
So to pull this all together, what LLaDA 2.0 has shown is that you can scale this superior parallel decoding dLLM architecture all the way up to 100B parameters. And they did it not with brute force training, but with this ingenious systematic conversion of existing models, which ensures they'll...
I'll leave you with. Okay. Both LLaDA 2.0-mini and LLaDA 2.0-flash have been open sourced. So if smaller institutions and research groups can now take foundational AR models and systematically convert them into faster, more deployable dLLMs using this knowledge inheritance idea, does this conversion technique fundamentally lower the barrier to entry for building cutting-edge models?